So today my plan is I will speak about a little bit the general view of deuteron-deuteron reactions. So here everybody is expert about DD reactions, so no need to go to detail. And then I will speak about direct reaction and compound nucleus contributions for DD reactions. Of course, today I would like to present you very interesting experimental and theoretical results. And then, so how can we explain? So, and then I will speak about model-independent approach, so I mean T-matrix. And then Konrad already, he has spoken about new threshold resonance contribution. And I will speak about a little bit mystery of screening energy, because especially I focus on nuclear astrophysics. And this is extremely important for nuclear astrophysical scenarios and especially for giant planets, white and brown dwarfs. And then the last title will be about a new material promise for future energy, and then will be discussion. Okay. So Konrad already explained. So for DD reaction, we have three exit channel: neutron channel, proton channel, as well as we have helium-4 channel. And the problem is for DD reaction, the Coulomb potential, Coulomb barrier, and I guess close to 450 keV. But you see here the energy spectra, the target is tantalum, and the beam of deuterium beam energy is 10 keV. And you see here very nice and beautiful spectra, and you see here proton, triton, and helium-3 channel. Okay, so I will speak about a little bit deuteron-deuteron gas target experiment, because this is really important for us. And you see here at the low energy, because of the Coulomb barrier, the cross sections drops very sharply. And then if you look at the differential cross section, this experiment was done by Brown and Jeremy in 1990, very famous experiment, gas target experiment. And you see here the neutron channel is higher than the proton channel. And if you look at the graphics, you see here at 19 degree, differential cross section is symmetric around 19 degree, because the target and the beam is already same. And if we look at the formula, angular distribution formula, you see here some coefficients, A coefficients, B coefficients, and C coefficients. DD reactions are special reactions, because below 100 keV, we have not only S and P wave, we have already D wave contributions. If we set C as a 0, so A coefficient represents S and P wave contributions, and B is P wave contributions. But here I would like to focus the branching ratio. And here everybody knows that for branching ratio for DD reactions is close to 1. Okay, so I will speak about a little bit the S factor, and then I will combine all knowledge. And for astrophysical nuclear reactions take place below the Coulomb barrier, and the cross-section value is extremely small, between 10 to minus 10 and 10 to 18 bar. And so we need a cross-section, as well as also we need the S-factor parameterization. So why we need this one? Because from cross-section energy graphics, sometimes we cannot distinguish new resonances. And the procedure is here. For astrophysical reactions, the procedure is to make experiment at the higher energies, and then extrapolation to the astrophysical energies. However, but here the extrapolation sometimes could be dangerous, because in this area, in this region, there could be some unknown resonances, as well as subthreshold resonance. And you see here for DD reaction, the S factor graphics depending on the energy of deuterium, and the formula is, you see here, the S factor corresponding to energy, sigma E cross section, and eta is here Sommerfeld parameters. Once again, I would like to show you one graphic. In here you see the neutron channel, the differential cross-section of neutron channel is higher than the proton channel. And so what is the reason? So I will explain the next slides. And our main title is here. So as I already said, the branching ratio for DD reaction close to 1. However, and you see here experimental results for strontium and lithium shows unusual behavior. If you look at this graphics, so below 15 kV, the downside, the branching ratio decreasing. So what is the reason? And then corresponding to decreasing, the anisotropy below the 15 kV, anisotropy is increasing. So why? This is a big question. So what I want to say, so some materials shows usual effects. I mean, the branching ratio is close to 1. However, for example, for some unusual materials, for example, strontium, lithium, the branching ratio decreasing. So what is the reason? And another problem is, you see here the screening energy problem. Konrad Czerski already mentioned. This is especially very important for nuclear astrophysics, as well as the neutron stars, and mechanism and understanding of neutron stars, as well as piconuclear reactions. And you see here the experimental values of screening energy is 2 times higher than theory. So always very big questions, trouble questions. And also I would like to mention here one very important thing. So if we know the branching ratio mechanism depending on the materials, so this is very important for us. If we use DD reactions in the future as an energy source, so we have one problem. The problem is the neutron poisoning. For example, for especially I know that NASA works this kind of projects, and if you have more neutrons, so we have more shielding, and this is a really big problem for space mission. Also for crowds, space crowds, and also working people somewhere, and neutron radiation really will be dangerous for them. So therefore, the mechanism of branching ratio is very important for us, for especially technological applications for space missions. Okay, so in order to understand this unusual behavior, I have started to investigate DVBA calculation. DVBA is distorted wave Born approximation. It means direct reaction contribution. So I have calculated branching ratio and anisotropy using by DVBA. In order to make a calculation for DVBA, we need optical potential parameters for entrance channel and exit channel. And the potential here described as a real potential plus imaginary potential. And real potential is responsible for scattering, and imaginary potential is responsible for absorbing. And you see here the angular distribution, the formula, of course, depending on the matrix elements. And if we integrate all of them, we can get very easily the total cross-section. However, when we look at our DVBA results, you see here, for branching ratio and angular anisotropy calculations, so DVBA could not explain this unusual behavior. So we have already published this one, but the problem is, once again, direct reaction contribution could not explain unusual behavior. So we need extra steps. Okay, if you remember, I have spoken about differential cross-section. You see here, the neutron channel was higher than the proton channel. The solution is here. So for DD reaction, the threshold energy is 23.8, and you see here for close threshold we have 2 isospin two isospin, two energy levels, very close to threshold, 1 minus, 1 minus. However, isospins are very different. So also these differences comes from here. Okay, so we need to pass another calculations in order to explain unusual behavior. So I moved to model independent approach. This is T matrix calculations. And you see here neutron could be in three phases, so spin states, singlet, triplet, and quintet. And this model is model independent approach, and you see here the PL. PL means the penetration factor. FL here represents regular Coulomb wave function, and GL is irregular Coulomb wave function. In order to calculate penetration factor, we have already written a new code, and then you see here the matrix elements. So all of them, we have written a new code, and then we did many calculations. You see here the coefficients. Also, we have calculated the S wave, P wave, and D wave contributions for DD reactions. And you see already here all contributions for DD reactions. Okay, so if you come to results, so here for neutron channel, proton channel, and branching ratio I presented here, and you see here also model independent approach T matrix could not explain unusual behavior. So also you see here the Hale R matrix parameterization. We have included also this calculation. So DVBA, T matrix, R matrix, so all now theoretical models shows the same behavior, so equal to 1, close to 1. Okay, so up to now we couldn't explain this unusual behavior. So what we need extra theory. Also here I will speak about the screening problem very shortly. Conrad already explained, but in here, so I take this page from NASA webpage. So when we are speaking about fusion, of course we don't speak about just only cold fusion. Also, so for fusion research, so already now 3 methods. One is lattice confinement fusion, another is a magnetic confinement fusion, tokamak system, and another is also already now laser fusion. But I would like to compare, because the lattice confinement fusion has a really big advantage. If you look at the problem is here, you see for density 10 to 22 for lattice confinement, for magnetic confinement and inertial, for especially if you compare magnetic confinement 10 to 14. So we have really lucky if we work about lattice confinement fusion, because we have the screening energy. So already our colleagues described, because of the surrounding electrons in the crystal lattice, the electrons could reduce to Coulomb barrier. So we called as a screening energy, a screening effect. And of course, at the low energy range, we should also think about the penetration factor, and we should include the screening energy to the penetration factor effect. And then we have already enhancement factor, so it is described screening over the bare cross section. Okay, maybe I would pass here. Okay, so what is the solution? So the solution is a hypothetical zero-class resonance, Conrad already have mentioned, in helium-4. So we offered a new resonance, threshold resonance contribution. And then also now you see we have a lot of experimental and theoretical evidence for this new resonance. And then of course this is a zero-class resonance, so we should think about we should make some new calculations, we should get new formulas. And the cross-section here comes from flat and the resonance contribution. And the flat contribution is here 1/3 magnitude. Okay, so you see here our formula. So it is too much things. So if I go to detail, I guess time will not be enough. However, so you see here we have two beautiful formula. for branching ratio, and for anisotropy. So for many theoretical, after theoretical working, so I would like to show our results. So for neutron channel, you see, if we have the usual materials, if we have usual materials, so we applied this formula, and then if we have unusual materials, and you see here our formulas explain usual and unusual materials for branching ratio also as well as anisotropy. And then you see here our resonance parameter for DP and DN channels, and here phi pi and phi n is the phase shift. We have already calculated, and then of course first of all I used Professor Schick's parameterization and for phase shift. And then our phase shift very close each other, and then we have got new results, new resonance parameter, new widths for neutron and proton channel, as well as Kornachelski applied this formula already published for zirconium target. Okay, so in here especially I would like to speak a little bit. Konrad already mentioned and explained, but you know already in the metallic crystal structure, of course oxygen contributes to screening energy. You know, also I should mention here the Thomas Fermi formula. This is really very important for us. And here M star mean is reduced effective mass. This is really very important for understanding mechanism. Okay, so the last slide. So this is my poster presentation. For the first time, I present a new material, mesh material. You know, mesh material is something like metamaterials and negative refraction. And then in my poster, I explain how can we create this kind of material, and this is very interesting results. And you see this screening energy is 7.4 kV, and the cross-section increment is very huge, extremely huge. So in here I used Pendley effective electron mass theory. So for the first time I suggested this material. So I guess this material could be hope for future. Thank you very much for listening.
Okay, now open for discussion, and time is limited only for 2 questions, please. Any question? Yeah.
Well, one thing, in the very low energies, your neutron cross-section is lower than proton cross-section, water enhanced, which I just missed, which is larger.
I'm sorry, I didn't understand your question.
Yeah, neutron channel is larger, or the proton channel is larger.
Okay, I will show you this picture again. So you see here, you speak about the branching ratio, yes? You mean?
Branching ratio.
Branching ratio.
Yeah.
So you see here for strontium and lithium, the neutron to over proton ratio.
Yeah.
And then neutron to proton ratio is decreasing, below the 15 kV.
Neutron to proton ratio, neutron is lower, smaller than proton.
Yeah.
And how about the experimental condition? I mean, the lithium and the strontium is very easily liquid-like, and melting point is very small. And whether during the bombardment, when the reaction, the region where the reaction occurring might be not a solid or liquid. That's
Okay.
one question.
Okay, thank you very much.
Okay, last question, please.
A very interesting idea on the metamaterial. What is the physical scale of the metamaterial, please? Can it be measured?
Material scale? You mean target?
The metamaterial at the end.
Metamaterial.
What is the scale?
This is very...
Pentameters, nanometers?
This is nanometer. Because nanometer, yeah. So in here, because we can depend the effect. Once again, maybe I would like to show you. I have speaking about the Thomas Fermi formula, and you see here the Thomas Fermi screening depend on electron mass and N. N is electron density, and I used the Pendelis experimental results. So I applied and I extracted new formulas, and then I applied this one, and so in nanometer dimensions we could create this kind of materials, very thin materials, something like 20 or 30 nanometer.
Thank you.
Thank you.
Okay, thank you. And time is over. And we start the next. Thank you.
Thank you.